That's great. Thanks, Malavik, and thanks for inviting me to give a presentation, and hopefully sometime I can visit in person as well. So today I'm going to talk about composite materials, including porous materials, the design for novel energy harvesting and creating sensing structures. So I'm in the Department of Mechanical Engineering at the University of Bath in the Materials and Structures Centre. And hopefully I'll give you a nice sort of simple overview of the work I've been involved in the last sort of 5 to 6 years. So the materials of particular interest to me at Bath are ferroelectric materials. So these are materials where you can switch the polarization with an electric field. So analogous to sort of ferromagnetic materials that you switch with the magnetic field. And these tend to be ceramics. Tend to be ionically bonded. So here we have a PZT material, lead zirconate titanate. And when it's at high temperatures, and when I mean high, I mean above the Curie temperature, maybe 300 degrees C for this material, it's cubic. And so we have a symmetrical unit cell. But if we cool the material down below the Curie temperature, certainly to room temperature, we get a phase change and we have a tetragonal material now. And we have the lead 2+ on the corners, the O2- on the faces, and then the titanium 4+ or the zirconium 4+ is now slightly displaced from the center. In this case, it's displaced upwards. So this creates a net positive here, net negative. So we've got a dipole, and that's really the key to getting some piezoelectric response. And this dipole can this titanium 4+, for example, can move up, down, left, right, and in and out of the page. So we've got 6 polarization directions for this phase of the material. In reality, there's other phases because the PZT, lead zirconate, it's an alloy in a way. So we have rhombohedral, which again is asymmetric, and there it's along the sort of 1-1-1. Directions. So we have 8 polarization directions along the diagonal, and surprise, surprise, the most active materials in terms of piezoelectric and ferroelectric response tend to be along this sort of morphotropic phase boundary, where it's a little bit tetragonal, a little bit rhombohedral, and you have 6 + 8, you have 14 potential polarization directions to take advantage of. There are those are ceramics, and that's my key area, but there are ferroelectric polymers. In this case, obviously, there's not an asymmetry in the crystal structure. There you have a stretched polymer chain, so a crystalline material. So PVDF is a classic example. So this, because of the fluorine, it'll be net electronegative. We have H hydrogen here, so net electropositive. And again, that's the origin of the dipole, which we can switch with an applied electric field. That's why it's a ferroelectric material. So asymmetry and some sort of dipole that's created that then leads to a net polarization. For example, you sinter them at high temperatures, and then they're cubic at high temperature. And we have, so I hope my internet's okay. So we have a material, and as it's cooled down, we will have a random orientation of the dipole. No reason for them to align in a specific direction. And in fact, the lowest energy state is a random configuration. And in this case, it won't be piezoelectric at all because there's no net polarization. So what we need to do to these materials is to pole them, and that involves applying a high electric field, 1 or 2 kilovolts per millimeter, a little bit of heat to allow those dipoles to switch under the electric field. And then we align the polarization directions, we align the dipoles within a common orientation, and then we cool it down to room temperature with the field applied, and then we take the field off. And basically then we've frozen in a net polarization into the material. And certainly piezoelectric materials are those sorts of materials. And the ferroelectric materials I've just discussed are a subset of piezoelectrics and pyroelectrics. So these are materials with that dipole that you can switch with an electric field. So you can switch the orientation of that titanium 4+ up, down, left and right by applying a field. That's different to materials like quartz, where you can't switch the polarization. It's asymmetric when you compress it, but you can't change the polarization by an electric field. And that's exactly why single crystals need to be used, and why you have specific sort of single crystal cuts for those materials. And so the attractive part of the ferroelectrics is you can create your shape, create your body, and then polarize it in the direction that you want afterwards without having to cut crystals, for example. So once you've poled the material, what can you do with it? Well, you can use the Converse piezoelectric effect, and that's to extend or contract the material. So by imagine our material now is one large dipole in a way, because we have a common polarization direction. We apply a negative and a positive, apply our potential difference. This will extend the dipole. So you can imagine that titanium 4+ moving further away from the center. And so we get an extension. If we reverse the polarity that we've applied, apply an electric field in the opposing direction, and we now push that titanium 4+ back into the center. So now it's becoming more cubic in a way, we get a contraction. So we can use it as an actuator. Just to note, these strains are small, they're ceramic, so it's high stiffness, so they're high force, but small displacement. And a good example, a good sort of rule of thumb is about 0.1% for most of the polycrystalline materials. So I think of it as a micron per millimeter. So if you have a millimeter of materials and you apply the maximum electric field, you get a 1 micron. Obviously, then you can do the opposite, and you can use it as a sensor by applying a mechanical load, so a compression. So again, you're pushing that titanium 4+ back into the center of the unit cell, and you're reducing the polarization, and it's that reduction in polarization that leads to the development of charge. And if it's a tensile load, you're increasing the polarization, and that will also lead to the development of charge and a current flow in the opposing direction. Again, it's just as a rule of thumb. So the charge that you can imagine that's being generated, this is a common PZT commercial. So the D33, so charge per unit force, is about 590 picocoulombs per Newton. So low charge, but you can accumulate that if you're interested in energy harvesting, and you can certainly use it as a sensor if you're interested in sensing. This is just out of interest, because I've always thought I understood the actuation part. You're extending the dipole, but how does the application of a mechanical load to an insulating ceramic actually lead to the creation of a charge? And so the way to really think about it is that if we have our polarized material that's been poled, and so we have a net positive, net negative here. So these are these dipoles that are aligned. And if we now paint an electrode on those polarized surfaces, you'll collect sort of screening charges in a way to balance out the surface charge on the material. If I now compress the material, I'll reduce the polarization because I'm pushing the titanium back into the center. And so the polarization falls. So some of these surface charges are now free to move in an electric circuit. And so I'll get a current flow. And likewise, if I remove the stress or I apply a tensile load, I'll enhance the polarization again. And again, charges will flow in the opposing direction to balance that charge. So there's nothing really coming out of the material. It's really the surface screening charges that are leading to the generation of the current or the voltage, open circuit, or the charge that's being created. And the applications, well, luckily we're all moving to electric vehicles, but diesel fuel engines, they are fuel injected, and the injectors, they are piezoelectric, very small, but very precision displacements. If you've had a greeting card that's sung a tune when you've opened it, it'll have this brass plate here. It'll have a ceramic on it that's been polarized, and then that ceramic will induce bending, and that will create the sound. You can do lots of small displacements rapidly at high frequency because it's a dipole, and so you can accumulate displacements. So ultrasonic motors are an application, Doppler ultrasound, so those running at 100 megahertz easily enough because you can oscillate that dipole to transmit, but also remember you can receive the signal that's coming back by using the sensing functionality as well. And if you've had a speeding ticket or been caught speeding, yes, there's a camera, and yes, there's a sort of optical method, but you'll also see strips on the road, and those are piezoelectric sensors that get the more accurate measurement if you want to query the speed. As an example, so in energy harvesting, so we do a lot of work in that, and a classic example is low power applications. So this was some work with a company on a tire energy harvester. So you attach a piezoelectric element to the tire, and the task was really to see how much energy you can produce, because you need to power the tire pressure monitoring system, which is sort of battery operated, and certainly 1 milliwatt can be generated, which is enough to power that battery is sufficient. I always thought it was all low power, milliwatt range, but actually there's you can take a look online, there's a company in France, Pythos technology, and they're working in the realms of hundreds of watts or even kilowatts for sort of renewable applications. So these must be very large piezoelectric structures that are responsible for that if they're using those materials. And just some basic parameters. So if we take our poled material and we apply a compressive stress, well, my charge is the charge per unit force, the piezoelectric coefficient times force. That's very simple to calculate. I know Q is equal to CV, did that at school. I know the capacitance, my device, its area times permittivity divided by thickness. There's a dielectric sound, it's a density material. And so my voltage, using simple equations, my voltage, so that's why it's a sensor. My voltage is proportional to the height because the charges are more created on the surface, remember, are more widely separated. But for a fixed dimension, fixed stress, the material properties of interest are the charge coefficient divided by the permittivity. So that's really what I want for that application. So I think a point to note is the open circuit voltage is proportional to the height and these material coefficients. And for energy harvesting, we can just take that a little bit further. Again, very simple equations. This was the equation that I derived for a good sensor, piezoelectric, and that's what we want in terms of material properties. But remember, the energy is half CV squared. And so again, I can use my very simple equation. So the energy is proportional to the volume, A times T. It's now proportional to stress squared. But for a fixed volume, fixed stress that I'm harvesting, the materials properties are the D33 squared divided by permittivity. So that's what I'm interested in. How do we develop better materials for better sensors, but also better energy harvesters? So these are the figures of merit that we like to use for sensing and for harvesting. People always ask me, what about efficiency? I think that's good to look at. So the efficiency of the system, we can imagine squashing my piezoelectric element and creating my energy. So I can think of it as the ratio to the electrical energy stored or generated divided by the strain energy that we've put in. And this is the equation that I derived earlier. And then this is just simply the area under the stress strain curve. So my coupling coefficient, that's the term for this parameter, is D33 squared divided by compliance times permittivity of the material. And just out of interest, for PZT, that coupling coefficient, K squared, is about 0.5. So about half of that mechanical strain energy that you put in is converted to electrical energy. For single crystal materials, ferroelectrics, that's up much higher, that's up to about 80%. So a relatively efficient means of converting strain energy into electrical energy. So I'm gonna, now you've got the basics, hopefully you'll understand everything that I do. So look at porous materials and pyroelectric composites. So let's look at porous materials. I've been working on these for a relatively long time, initially for hydrophone materials, because I used to work at DERA, Defense Research, on sonar, but also recently on energy harvesting applications. And remember that polling process? And so we have nice models to look at our porous materials and model that polarization process where the dipoles are orientating in the same way. And the reason we do that is that if we introduce porosity into a ferroelectric, the pores have a very low permittivity, relative permittivity of 1, whereas the ceramics, the ferroelectric ceramics, are very polar, and so you have permittivities of 1,000 or 3,000. Now, when you apply an electric field to such a composite in a way, the electric field will focus in on the low permittivity phase, namely the pore. So that's a consequence of Gauss's law. So in a way, that's a challenge, because we want the electric field to be in the ceramic, because we want to align the domains. So we certainly create these nice models that predict the polarization and then the effective properties after the polling process. And the first sort of work that we did in the energy harvesting was a PhD called James Roscoe. He looked at the piezoelectric properties as a function of porosity. So this is the D33 coefficient. So just remember, this is the charge per unit force against density. This is barium titanate. That's a common ferroelectric ceramic. So the dense material has a piezo coefficient of about 120 picocoulombs per Newton. But then as you introduce porosity, it falls. But the key point is it falls gracefully. It falls slowly, and that's because of the challenges of polling the material as you introduce pores. But the permittivity, because the pores have a much lower permittivity of 1 compared to the ceramic, which is what, a dense 1600, at 50% porosity, for example, it's fallen quite significantly, while at 50%, the D33 has fallen only slowly, gracefully. And so your figure of merit, remember, for energy harvesting, if this stays quite high, but the permittivity falls a lot, then you'll end up with a better harvesting figure of merit. And so you'll end up with a better energy harvesting material. James looked in the literature and scoured the data, and there was various data on porous materials, not for energy harvesting, for other reasons. And you can see that as you go from a dense material to a more porous material, the figure of merit for energy harvesting went up quite a lot. In this case, it's up by a factor of 5. So by introducing porosity, and this tended to be random porosity by adding filler particles that then burnt polymer spheres, we can certainly go from figures of merit from around 900, just think of it as an arbitrary value in a way, because the energy is proportional to this value, to a porous materials by a factor of 3 to 2,700. But you can see there's a lot of variation in the values, and that's because of the random nature of the porosity, and they're quite large pores. How do we improve on that and get even higher figures of merit that get low permittivity, but also high piezoelectric coefficients? And the answer is quite simple in a way. It's pretty obvious. I think you would have worked it out in many senses, but this gives us some numbers within a model. If we think of a pore within my ceramic matrix, remember the electric field concentrates in that low permittivity pore phase. And if I try and polarize the material, to pole the material through thickness, what happens is that you get low fields on the top and bottom of the pore, and you get high fields on the sort of left and right. So as I'm aligning my pore and I'm making it more anisotropic in its geometry, increasing the aspect ratio, and I line it in the pore direction, I'll get better polarization. And if I align the pore at increasing angle to the poling direction, then I'm going to get less poling of the material. So what this is doing is really stating that what we would ideally like for a highly polarized material, so we can get that D33 coefficient as high as possible, are highly at high aspect ratio pores that are aligned along the polarization direction. And luckily, Dr. Yan Zhan had a Marie Curie fellowship to visit Bath about 6 or 7 years ago, and she was studying freeze casting as a means to make materials. And this is exactly the sort of ceramics freeze casting could produce. So it's a very simple process. You take your ceramic particles, powder, you disperse it in water with some binder, some dispersants. You then freeze from the bottom, and then the ice crystals grow directionally. So you have your ice crystals. You then have some freeze drying process to remove the ice, and you end up with a nice sort of a highly aligned porous ceramic, which you then sinter to densify those ceramic regions. And it's very easily done. You could scale it up. You can change the ceramic fractions, water fractions. You can start to freeze in all sorts of directions as well, make complex structures. But the exciting thing about it at this time was that you can align those pores in a common polarization direction, which is exactly what we wanted to do. And also you can make molds, because obviously you can just 3D print a mold now. You're just freezing it within a mold. You can start to create simple shapes, individual elements for sensing, and also you can embed a polymer into the pores, and surprisingly it's also relatively flexible. And the outcome of that is that you get a more consistent material, but also you increase the degree of polarization. And so that D coefficient is much closer to that of the dense material, but you can still drop that permittivity by filling it with pores. So you go up another factor. So now you're at the factor of 4 in terms of the figure of merit. So it's a better material for energy harvesting. I presented this a lot, and then everyone used to say, well, that's fine, but that's a figure of merit. I still can't believe it. You're taking a dense ceramic, you're removing 50% of the material, if it's 50% porosity, and you're telling me it's generating more energy. How can that be? So, well, it's because of this, because you've reduced the permittivity while maintaining the piezoelectric activity. So as an experiment, we thought, well, we'll just make a mini energy harvester to prove that it works. So here's a little shaker, and there's a ceramic here with a mass on top. So we're applying a force, oscillating force. We take a variety of ceramics of different porosity, and we make them the same volume, same mass, so it's the same stress. And then we just use a rectification to charge up a capacitor to accumulate that charge that's being generated. Here's the results. That's fine, just checking the time. Here's our voltage against time. The dense is the red material, and the blue is the most porous material, 55% density. So the voltage has gone up. That's because remember that sensor coefficient, D33 divided by permittivity. So that's gone up because of the introduction of porosity. The current will go down. So this is the short circuit current. The current will go down, but that makes sense because the current is just related to the charge. So the D33 is falling a bit, and so will the current. But the net result is that you do generate more energy. So this is the voltage on the storage capacitor. The dense material is here, whereas the most porous material ends up with more energy and a faster charging of the capacitor. And the intermediate density is somewhere in between. So going back to efficiency, this is what confused me for a lot of time, because I thought, well, okay, so if I'm getting more energy, is the material more efficient? And if I derive and look at my coupling coefficient, remember it's this equation, electrical divided by mechanical. Well, that's staying about the same. The permittivity is falling. So, but my compliance, my stiffness is also falling, and it's falling quite a lot. So actually my porous materials, I am pretty sure, but it's very difficult to measure this, I'm pretty sure it's less efficient. So even though I'm generating more energy, electrical energy, how is it that my material is less efficient? That doesn't seem to add up, does it? Well, remember, the coupling coefficient is the efficiency of the strain energy that you're putting in. So if I imagine my shaker test is at a constant stress, because that mass is the same. If I have a very stiff, dense material, then my strain energy that I put in for a certain level of stress is relatively low because I have a stiff material. My porous material is less stiff, and so for a given stress, I have a higher amount of strain energy within the material. So I win out on energy harvesting in terms of energy, but actually I'm harvesting a lower fraction of the mechanical strain energy. But it doesn't matter for energy harvesting, because all I need is more power for my electronics rather than efficiency. Oh, I'll just put a few things about novel structures. So remember, the challenge is to polarize these porous materials. So we had an idea of making a sort of graded structure where we have an internal porous layer and some more dense outer layers. And that was a combination of looking at the mechanical strength, sort of ease of applying electrodes even to the material. And what we found that these were even better performance. And we tried working out and using our model to understand why these were behaving much better than we anticipated. And that's because, again, this polling process. I won't go through all of it, but basically, this is my porous inner layer. Remember, it's a low permittivity region, and so the electric field will focus into the porous inner layer when I'm trying to pole it. And so that means I pole this region very well, but there's not much of it. When my inner layer is very thick, the electric field is far more even, but it's harder to polarize because I have no sort of concentration mechanism within my sort of multi-layer structure. So there's a balance between these two extremes. And so when I have an intermediate layer of a sandwich layer and a dense top and bottom, I have a higher field in this lower permittivity region. That helps with poling. And so I get better poling by focusing my field in that region. And also I've got a lot of it because it's thicker. And so there's a balance here. And by doing that, I actually got much better properties, even further in terms of this figure of merit again, compared to a randomly distributed material. Okay, so I'm doing fine for time. Yeah, about half past. So I've got 15 minutes to finish the second section on pyroelectric applications. So this is very much the same theme. And in this case, it's not stress. So the piezoelectric properties are related to a stress-induced change in polarization. All a pyroelectric effect is a change in polarization with temperature. And so in this case, we can use the material as a temperature sensor. So if you've walked to in front of a door and it's opened up, and when you've walked into it, because there's a infrared detector, that will have a very small pyroelectric element that's polarized, and your body heat is sufficient to change that polarization and release charge and let the door know that you're standing in front of it. And the mechanism is exactly the same as the piezo. It's the polarized material, surface screening charges. Your heating will reduce the polarization, and that will lead to the screening charges on the top and bottom being free to flow in an electric circuit. And I think a key point here is that if you're thinking of a current, well, that's dq dt. So what you want is rapid temperature changes to get a high current as well as a high pyro coefficient. And they're a subset of piezoelectric materials, and the ferroelectric materials are of interest again to us at Bath because the ferroelectrics are both piezoelectric and pyroelectric as well. Just a few examples. So Daniel Zabek was a PhD student, wanted to try and make more responsive materials for sensors and energy harvesting. So this was PVDF. There's a ferroelectric polymer, remember? And he wanted to sort of harvest sort of heat. And his view was that you had aluminium electrodes, which was reflective, so it didn't allow any heating of the material. So what he wanted to do was open up windows into the surface of the electrode to allow infrared radiation to get in to heat up. But of course, if you've got less electrode, maybe then you're not collecting those surface charges. So there's a balance between those two effects. And he created a variety of structures. So these are effectively the windows in his electrodes to basically let the infrared radiation heat into the material, to heat up the material. And he then tested his variety of samples under a lamp that basically turned on and off, on and off. So this is the temperature with time. So this is the 100% means a fully covered electrode. And you can see it's a lower temperature and it's oscillating. So it's oscillating what, 1.5 degrees C, but by opening up those windows into the electrode, then he gets a greater temperature fluctuation with time. How does that relate to voltage? So this is the open circuit voltage. And you can see here, again, fully covered. You ended up with a lower voltage, primarily because of the lower temperature. And by going up to a more porous sort of electrode in a way, so allowing that infrared in, then the voltage was higher. And you can see why this is used as a pyroelectric sensor. So this is what, 50 microns thick of PVDF, so a very thin layer of PVDF. You're only changing the temperature by 2 degrees C, but you're generating a 60 volts potential across the material. People report that and say the world is saved. That's a huge amount of voltage. It's loads of energy, but of course that's not energy. That's no current flowing. So you also need to know, as well as the open circuit voltage, what's the short circuit current. And you can see here, again, you get more current flowing because the rate of change of temperature is higher and the actual temperature difference is higher. So you get more current as well. But the current is down here in the nanoamps. So very small current, high voltage. That's very typical for sort of piezoelectric and ferroelectric materials. And whatever you do, if you're interested in the energy, don't multiply the open circuit voltage by the short circuit current. Some people do it. It's just plain naughty. Don't do it. But you need to dissipate it through an electrical load. Yeah, and the outcome was that by putting in those windows, actually this is a fully covered material with that aluminium electrode. By having about 45% coverage, by opening up those windows, the voltage and the current increase. So it's a better sensor in terms of pyroelectric detection. If you start putting in too many windows in, then obviously then you're not collecting that charge, that surface charge that's created on the surface. So then it begins to fall. So there's a balance here. And we found that this is an appropriate sort of balance between those two sort of tensions. Some people, we still do a little bit on using pyro for energy harvesting. It's maybe of interest, but you're harvesting temperature fluctuations. So this is just really that derivation that we looked at earlier for vibrational harvesting. For thermal harvesting, there are many problems. One is that you can imagine something vibrating at 50 hertz, 20 hertz, natural vibrations of structures quite easily. Natural thermal fluctuations tend to be much slower. So you're inherently going to produce less power. But also, if you look at the efficiency, I can derive a similar sort of efficiency factor by looking at the electrical energy generated from a temperature change, which is here, divided by the energy that I need to put in to induce a certain temperature change, delta T. And this then becomes a sort of an efficiency factor. And you can see there's lots of parallels between vibration and pyro, because it's essentially the same process. So it's proportional to stress squared, proportional to delta T squared, inversely proportional to permittivity. And when you do that calculation, that efficiency is much, much lower, less than 1%, and it's dependent on the actual temperature as well. The actual reasons, a nice simple reason why this is inefficient and this is efficient, I still don't know. So if anyone has a good reason, because they're both the change in the polarization of the same material. So if you do have a good answer, let me know. And in terms of energy harvesting for fluctual thermal fluctuations, we thought, okay, so it's at low efficiency and there's not many thermal cycles, but we thought maybe what we can do is to directly couple my pyroelectric element to an electrochemical system. So rather than storing up charge on a capacitor, because it's very slow, for example, and there's not much of it, can we couple that to an electrochemical system, such as water splitting? So here we have a bit of ceramic that's oscillating in temperature. We rectify that current because it's going an opposite way. So we would produce hydrogen and oxygen on the same electrode. Well, we only need 1.5 volts to split water. And we saw that 60 volts was easy, even on a very thin piece of PVDF. So the voltage to induce or start the process of water splitting, that's easy. So that's easy to produce. But obviously with Faraday's law, to create a mass of hydrogen, that's nothing to do with the voltage, that's the amount of charge. So what we want is high voltage, it's over 1.5 volts, but also we want as much charge as possible. But we thought, well, let's try and see if it works first. And this is a bit of ceramic that's being heated and cooled, thermally cycled. So it's changing about 2-3 degrees C. It's a ceramic element. So the voltage is plus or minus 5 volts. So that's easy. Remember, it's rectified in the end. And then we attach that to a little sort of water splitting cell with some microelectrodes, and it works. I won't play the video because they never work on Zoom. So you can just barely see a few bubbles, very tiny. I think as I get older, I find it harder to see them as well, but they are there. And over time, the hydrogen builds up and it's in 2 to 1. So we're definitely splitting water, but it's not much. That's the key. And they think, okay, how can we improve the amount? Well, if you look at the basic equation and Faraday's law, we need charge. So we could somehow generate materials with higher pyroelectric coefficients, but that would need an enormous increase. We could maybe increase the temperature range rather than a few degrees C, but again, you're sort of almost limited by the temperature of water. But maybe we could increase the area. And we thought about buying some bigger and bigger plates of material with more and more surface area in a way. But a group from Hong Kong, Haito Huang's group, what they actually did was take nanoparticles of the material and just placed it in water and then subjected the nanoparticles dispersed in water to temperature fluctuations. And of course, compared to a ceramic element, you can get enormous changes in area. And so there's it's certainly a whole series of people working in this area now, looking at thermal fluctuations or vibrations and generating charge and seeing its effect on electrochemicals. So that's moving away from a device and put it directly within the system. And just out of interest, I think this is the last, last final couple of slides. It's good, I got 3 minutes. So remember that Curie temperature that I discussed when it was cubic to tetragonal. So this is the polarization of that material as I approach the Curie temperature. So here it's tetragonal, here it's tetragonal, it starts to change phase to cubic. And so we get a dramatic change in the polarization near the Curie temperature. And so obviously if it's a change in polarization that's changing creating charge on the surface, an obvious experiment to do is to fluctuate your material above and below the Curie temperature. Most of the sensors are operating down here with small changes in polarization. That's enough for a sensor. But if you're interested in these applications, it's probably better to move above and below the Curie temperature when you're exploiting the large changes in polarization as it disappears and comes back. And that's something that we're looking at. And then just finally, this is more of a bit of fun in a way, but it's near the end. Over lockdowns, I was thinking about how any of this could link to what's going on in the pandemic. And I started to read a little bit about N95 masks, because there was a shortage of them at the time. And I didn't know this, but the N95 masks, the best sort of medical grade masks, are charged materials. They're electret fibers. So the polymer fiber is actually electrically charged, sort of corona poled before being inserted into the mask. And the problem with those is that the charge is not inherent in the material, and so it decreases with time, and you can't wash them because then that loses the charge. And that charge is needed to attract the smaller droplets that aren't blocked by the fiber mesh. So one thing I thought was, how about making a PVDF mask, a pyroelectric mask, in the sense that if you had pyroelectric fibers, because PVDF can be polarized, we've seen that even on the thin films, and what you would do is have pyroelectric polarized fibers, and of course then when you breathe in, you will cool the material, and so the polarization falls, and so you would develop a surface charge that would attract droplets. And then when you exhale, because we're all sort of warmer than the air, our air that we breathe out is slightly warmer, so we would heat the fibers as we breathe out, and the polarization will fall. And again, then you can collect that, and then as you breathe in again, you cool down. So you can use those pyroelectric charges. And I guess the potential advantage there is that you could wash these, because the Curie temperature of PVDF is about 120 degrees C. So it would maintain its polarization by washing it, certainly at 60 degrees C, for example. But that's certainly something a little bit wacky and maybe of interest. Okay, that's good. I've finished on time. That's good. So lots of opportunities. Porosity is good in ceramics. It's not always bad. The porosity I work on tends to be much larger scale than a lot of other people, sort of microns or even sort of hundreds of microns. But you can certainly use it to make better sensors, better pressure sensors, thermal sensors, enhance your energy. It doesn't seem to make sense. Removing the active material gives you more energy, but I've explained how, but also interacting with the chemical systems as well. And I write a lot of sort of review papers. I think I'm more of a writer than a scientist, so you're more than welcome to look at these. And if you email me, I can send you some. Thank you.